The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I have a two sets of handouts. If you don't get a copy, it's all on web. Okay, and if I do this well, every time you should get a handout. And my objective is for you to focus on listening and discussion, not to take notes. So it's either in a handout or you go, it's online. Okay, it's an experimental course. The first time I'm offering it, so it has a special, say, 2997 number, 6 units. If you look at the handout, if you printed it yesterday, I changed something, and one of the changes is very important. This course will be pass-fail basis. Okay, and what does it mean is if you are an undergraduate student, for example, in course 2, pass-fail could count for unrestricted elective, but it does not count for restricted elective. And if you are course 2A, it does not count for your concentration. Okay. And if you're a graduate student, this is not an H-level course. It's not an H-level course. So those are the, just for your clarification. And if you look at the handout, the syllabus, what we will have first is once a week at this time. And also, I have office hour. And I have a volunteer TA, Daniel is here. You can contact him if you have questions. If necessary, we'll ask Daniel also set up an office hour. And what else? I don't have a copy in my hand. Take a look. Thank you. In terms of the requirement, homework, the homework is every week I will assign one reading, and you will turn in your report, one-page summary of the reading. You can summarize what you understand, what you do not understand, and that's the. I do not say we're given actual number of homeworks, so it's a reading-based homework. And at the end of the semester, you will write a final report, project report, and the detail of the report will launch in the middle of the semester. Any questions? Okay. If not, I will start. Like I said, all the everything is online, and you can jot down whatever notes you want, but my purpose is not to have you write too much and focus on listening. I do not have a textbook on this. So let me start. So this course, if you look at the title, is direct solar thermal to electrical energy conversion technologies. There are a few points I want to emphasize. One is a heat-based course. Solar, thermal, this is all focused on the thermal aspect. The solar energy is, in this course, is a big, giant heat source. And the other aspect important in this course is direct energy conversion. So the focus is on how to convert the heat into electricity directly without the moving parts. And when I say the technology, you realize that we move on. Those technologies, some already existing, but clearly is not widely spread, used, right? It's not widely used. So they are still under development, and whether it will work out or not down the road is not completely sure, but say that's your opportunities. You're here to do research, future development, and maybe you will push some of this technology to real world. So I will start with this slide to make a case that it's important that we think about the heat. You can start either from the input side, look at how we are using all the energy. Fossil fuel or even nuclear, the energy source, from the energy source to convert this energy into electricity, into mechanical energy, you can say more than 90% is via heat, right? The mostly is the thermomechanical means to convert the energy into either mechanical energy or electrical energy. And the other aspect is look at the end use, how much energy is lost, right? And you count all the numbers there, you find out that more than about 60 to 70% of the energy are wasted. So what we are looking into is whether we can develop alternative ways to either use the input energy or convert some of the waste energy into electricity. Yes?
Is there 10% missing at the output?
10% missing, you have to look at some of this end here. Okay? Okay, we're talking about the heat sources, so just a few examples. If you look at the automobile, the driving efficiency as a measurement is less than 20%. Right? And if you want to remember, it's easy to say about 1/3 of the energy goes through the tailpipe, exhaust. The other third roughly goes to the radiator. Right? Those are completely wasted. So can we recover some of this energy? And in fact, this is challenging because it's mobile. You have to feed into the complex systems. And in those cases, it turns out people are looking at the various options, but say the mechanical way of converting those energy into electricity is not very feasible. So there are a lot of companies looking into thermoelectric, for example. And now you look at another way that we use energy is buildings. And give an example, in New England in the winter, all home furnace, boilers, most of the time they are on. Well, very often they are on, right? And those are combustion process, and at the end what we use it for? Hot shower. Heat up the room, right? That's a low quality heat source. Once you quench to this temperature, you have high temperature combustion, you quench to low temperature, just take a shower, and you are generating a lot of entropy. And in some regions, there are big coal-fired power plant or oil-fired power plant, right? In this case, people take this steam and supply the heat to the community. That's electricity heat cogeneration, cogen plant, right? But we don't do this at home. The technology is not out there yet. People are pushing, and in fact, there is say Honda is trying, for example, developing home standalone internal combustion-based system. But it's still not taking advantage during the combustion, during the heat up the hot water process. We are really generating a lot of entropy. We are wasting useful energy. So we develop technologies that can do home cogeneration. Industrial process, right? That's about another third of the energy that's used. And their heat sources of different temperature, very wide temperature range. Once I visited the aluminum smelting plant, so that's just converting aluminum oxide into aluminum. And the process is a high temperature electrochemical process. So you heat up aluminum oxide to melting state, and then you use an electrochemical way to extract the aluminum. And those plants are typically built just beside power plants, electrical power plants. The plant that I visited is a 500 megawatt electrical input. Okay, that's a huge power generation, power required. Just give an example of how much is 500 megawatt. A typical power plant is about 1 gigawatt. And the world solar installation, solar photovoltaic installation is about 6 gigawatts now. So one power plant, one aluminum smelting plant takes 500 megawatts. And of course, there is part of this aluminum oxide to aluminum energy is stored as chemical energy, but half of this is dumped into the environment as heat, right? And right now there's no technology to really recoup this heat into anything useful. So now you think about this is a waste heat, right? Renewables. When we think about the photovoltaic, solar, we often think about photovoltaic. But fundamentally, solar is a high temperature heat source. Anyone knows the equivalent temperature of the solar radiation coming to Earth? Close. It's about 6,000 Kelvin, 5,800, 5,800. Okay, and geothermal. Those are renewable. Those are heat sources, right? So, how can we use as a heat? And in fact, if you look at how people, what the people are doing now, the solar utilization, the biggest installation is in solar water, not in PV, just hot water. And I came from China. When I grew up, there was no hot water, so I didn't seldom take a shower, no water in the winter. And nowadays, when I go back home, we have solar hot water. And it was a really fundamental, life-changing technology, very cheap, but it's actually high-tech. So here I'm showing the solar hot water system that's widely used in China, and give say an order of magnitude. It's about a 100 million square meter installation. 100 million square meter. And if you take 100 million square meter, you take a solar energy, 1 square meter is about 1 kilowatt. And a thermal efficiency, they collect the heat around 60%. So you multiply this together, how much you get? You get about 60 gigawatt, right? Thermal energy being used. And I said as a high tech, this is a evacuated tube, vacuum tube. Okay. And so there's an inner layer, an outer layer, and in between is a vacuum tube. And in the inner layer tube, there's a coating. This coating will absorb the solar radiation, but it minimize the thermal radiation, and it's done very cheaply. In a typical tube like this high is only I wasted once a factory $1.5 tube. This big, all manufactured. So because of the low cost, it's widely used in developing countries. And of course, when we talk about the electrical generation, this is their installation in U.S. Creamer Junction, where the heat is from the sun is focused through those parabolic troughs, heat up the fluids, and these fluids are used to drive steam turbines. Okay, and there are also the power system that people are developing. Some are used in Spain and I think also Australia, where the mirrors focus and heat up the power here, and this goes to higher temperature. And the conversion is via mechanical systems. And the question, of course, so here in this course, we're not, as I said, we're not looking into mechanical energy conversion. We're looking into alternatives. And I just want, so some of those alternatives we're going to discuss. One is thermoelectric. In fact, Daniel, does that work? Yeah. If you can turn it on. So it's you will see that this is a conversion that, as long as there's a temperature difference, it can generate electricity. It's by solid. If you have used thermocouples, those are essentially thermocouples putting together. Right? Thermocouple, of course, we normally just want to generate the electrical signal, but in this case, you can also, if you make it efficient, you can convert it into electricity. The second, so this is here, the working fluids is electron. And in this demo, what we have is just a copper. Here is a heat source, right? Copper conduct heat to this side. The top side is hot. And there's this thermoelectric device, very thin. It's about 2 millimeter, 3 millimeter sandwiched between this copper and the heat sink aluminum block. And hopefully I don't see it, but once the temperature difference, there's a temperature difference, you'll start to see the LEDs lighting up. So that's direct, no movement parts, using electrons as working fluids. And the second example is thermionic energy conversion. How many of you know that in our department there's the microfluidic Hastabelos lab? Hastabelos. That's on the second building 3, second floor. Hastabelos was a professor in the mechanical engineering department, 1950s. And he developed this thermionic engine. So you can see it lighted up, right? And of course, you have to maintain this temperature difference. So if we burn it for a long time, the other side, the cooling is not quite there. The temperature difference will become small. Your power, I saw it before, it actually fluctuated before. But this is also another important aspect. It's a thermal system, so you have to put the heat in, take the heat out. And what the converter is small, but your thermal auxiliary system may be very big. So you have to do a good engineering design. But see, I was mentioning thermionic energy emission and energy conversion, and Professor Hastabelos started his PhD on thermionic engines. And he spin off thermal electron. If you drive 128, you probably see that company. Thermal electron, now it's called Thermo Fisher. Right? And the original purpose was to develop the thermionic engines. In fact, you go to read it, it's 1956 or 58, I forgot. In the 1950s and the 1960s, the efficiency was about 18% from heat electricity. But it's a very high temperature. So there are a lot of technological difficulties, and at the end they didn't pursue in terms of commercialization. Of course, photovoltaic, normally we don't think of it as a heat engine, but it is a heat engine. It's limited by the second law of thermodynamics. Okay? And in fact, any time we can get close to second law, you really have heat. And but see, this is of course using the photon from the sun, and there's another way is using the photon from a terrestrial heat source. Right? You have a home furnace, and you can use the photon from there to put a photovoltaic. That's called the thermal photovoltaic. So those are all ways. Some of the direct energy conversion, now moving parts here is using the charge as a fluid, and we'll be talking some of those technologies and the basic principles. And of course, when we think about the solar, the advantage, compare potential advantage, as I say it's demonstrated fully yet, is that in the case of photovoltaic, only the energy above the band gap of semiconductor is useful. But when you think about solar thermal, you can think about the full spectrum of the solar energy. So that's the this year we started actually Department of Energy Center looking into how we can advance those technology. One is solar thermal photovoltaic. So here the idea is I take the solar energy, absorb it. This is not directly onto photovoltaic cell, but absorb it to heat up this and re-emit photon. Why you do that? Because when you re-emit the photon, if you can do better control, you can emit photon right at the band gap of the photovoltaic cell. And theory says you can potentially get a really high efficiency and with a single junction cell, but no demonstration. So that's one of the direction we're looking in this center. And the other direction is looking into thermoelectric, just like what we come here. The temperature difference instead of the burner here, using the sun. Anytime you have temperature difference. And again, the K is how we can make this efficient, how we can make that low cost. So when you think about energy, the cost is the main concern, right? The photovoltaic cost right now is just too high, so most people are reluctant to put onto their rooftop. So that's the motivations for this course, and to really understand those technologies, we'll have to dive into, for some of us, then can we take this on? For some of us, this may be unfamiliar territory, particularly I think for mechanical engineers, because most of the time we are familiar with heat engines using steam, using molecules. And here we're talking about heat engine using charge, electrons, and solid. So we'll have to cover some of the basic the background knowledge in this area and understand the technology, understand the limitation, and I want to bring you to the forefront of research. What are people doing? Maybe you have new ideas in doing new things. Now, just to make another comment, this is a very different, right? You can say the dying down process is slow. Thermal has the potential to do storage, right? With the thermal mass, you can store the energy. Or photovoltaic, if there's no light, you immediately don't have any power there. So that's one potential advantage of thinking thermal. Okay, so now I'm going to move into really the first, what I want to use here is to review some thermodynamics and heat transfer And if you have taken thermodynamics, if you're ME, you will know some of the material. If you are from other department like physics, you also know some material. Both groups have some material maybe you're not familiar with. But my advice is just to take it. This is, I would say, this is my starting point for future discussions. So when we think about first law, the thermodynamics, we think about two laws. First law of thermodynamics, second law of thermodynamics. Right? We take a system and we define the boundaries. Right? So the boundary define our system, and across the boundary we have heat flow, we have work flow. And typical convention is that the say heat goes in, we take that positive, and work goes out, we take that as a positive. That's just due to convention. If you get a negative sign, it means your heat goes out or work goes in. And then we have closed system, means there's no mass flow across system boundary, or open system when there's mass flow across system boundary. In the simplest form of thermodynamics, the first law is just the energy balance, right? On the left-hand side, I have the energy of the system, the energy change, and on the right-hand side is the heat transfer into the system minus the work output. Simple energy balance. You can write it into differential form, or you can write it into rate form. And then you do heat transfer, you actually use the rate form most often. But I say, some of you may still remember what's important is to recognize on the left-hand side is a state property that does not depend on the process. On the right-hand side is process dependent. So it's actually very amazing. You take two process dependent quantity, you take a difference, you get a quantity that's independent of the process. Looks very simple, but this is a truly important aspect. And energy of the system, including kinetic energy, potential energy, and internal energy. Or if you have other forms of energy like elastic, magnetic, all those. And consider relation that we're using is specific heat, for example. And here, the specific heat is the temperature derivative of the internal energy. Here, the internal energy, I use a small u. It could be either per unit mass based or per unit volume based. Okay, so that's the first law. Second law. Second law was written into an equation, but it's not an equation. It's an inequality. And what we have here is the entropy change. Again, this is a state property. Entropy equals the entropy transferred across the system boundary and plus entropy generation in the system. Again, on the right-hand side, it's process-dependent, and on the left-hand side is state properties. That's independent processes. Right? Now, I think about the heat engines. The heat engine, when we think about engine, we think about cyclic motion, right? You don't want to design an engine only go one direction, doesn't come back. And so when we think about cyclic motion, during a cycle, any state property, right, go back to the origin. It's an independent process. Once it goes back, the change is zero. So here we just wrote entropy and energy, any other state properties. So if entropy change is zero, now what's the maximum efficiency you can get? And maximum happens when there's no entropy generation. So if there's no entropy generation, Sg is zero, and I look at this is my system. The heat in is positive, heat out is negative. So I have my second law written into left-hand side is 0, entropy generation 0. This is entropy transfer across system boundary, right? And this gives me a relation between the heat in and heat out and temperature of the two reservoirs. And if I use this relation, I go to calculate what's, in this case, what's the efficiency of this heat engine. You can see the efficiency, of course, we define as the work we get versus the price you pay, that's the heat in. Right? Efficiency here is the work. Now, the work first law tells you the work equals heat in minus heat out, because the internal energy during a cycle change is 0. So you can see you get the calorie efficiency, right? That's the maximum you can get for any heat engines operating between two constant temperature thermal reservoirs. People sometimes look down into heat engines. Say it's a heat engine, meaning it's a thermodynamics. It's not. You can't convert all the heat into electricity. That's correct, unless you have 0 Kelvin, right? But the important thing is you put in the lamper, and you see where we are. The heat engine is very respectful if you have even just a 200 degrees temperature heat source, and if you can get a calorie efficiency, 40%. Right? If you take the sun, 95%. Right? The modern thermal power plant is about 40%. I said automobile internal combustion engines, right? The driving efficiency is less than 20%, and the IC engine efficiency is probably around 25%. So, heat engine, if you can achieve the theoretical efficiency, you're doing really well. The problem is there are a lot of losses that limits us to get to practically get too close to the calorie efficiency. Right? So that's the what you learn in 2005 thermodynamics. Now I want to go to a little bit microscopic picture, because what's an entropy, for example. And so let's look at an isolated system. Isolated means there's no heat transfer across system boundary, no work transfer, no mass transfer. It's isolated. But I'm going to look at imagine I have the magic eye. I can look at the individual molecules, electrons in the system. Okay. And there are many different possible configurations. A molecule can say the molecules in the system could be at different states, different position, and each atom could have many different possible energy states. This is from quantum mechanics, right? So every possible configuration, possibility, you can go back and take two different color beads and mix them up. That's your experiment on this micro picture. And every possible configuration is a microstate. And let's suppose we know how to count what's the total number of those possible configurations. So the total number is omega microstate. Those are very big numbers. Okay. Now, what the basic principle of this microscopic picture says, every state is equally possible, equal rights. Okay, no discrimination. And so this is the equal probability principle. Every microstate is equally possible. And it's based on this, all the statistical description of the statistical thermodynamics is based on, starting from here. And what Boltzmann did is to relate this number of total microstate to interval. This was actually in Boltzmann tombstone. You go to Vienna. And this KB is the Boltzmann constant, 1.3. I don't remember any. There are people in physics, they use atomic units. I always remember things in say SI unit. So that's a difficult, large exponent, 10 to the minus third joule per kelvin. But it's good to keep some numbers in mind, okay? So that's the, like I said, a starting point for the microscopic description. And here we'll consider an isolated system. And now if you think about a non-isolated system, a system that can thermally exchange energy with the environment. And because of that, each microstate is no longer have equal right in terms of observation. The probability of this system, if you can observe this system in certain specific microstate that has certain energy E, and in this case, it's no longer equal probability. And we're not going to derivation, but you can go from here, equal probability, to construct an isolated system that made of your system and the environment. And with all that derivation, at the end, we get the probability of the system actually insert in one microstate. This is the one microstate that has energy E, is depending on the temperature of the system and the energy here, exponentially. Right? So you can say higher energy, less probable. And if you do chemical combustion or a lot of Arrhenius law, you probably learn in high school, right? That's this exponent. That's coming from here. Boltzmann statistics. And so here is a closed system. What if there is a mass flow, particle flow across system boundary? And in that case, this is similar, but there is an extra chemical potential uphill in the exponent. And this is say, constant temperature but open system. And mu here is chemical potential. What is chemical potential? Think about temperature. Temperature is a driving force for heat flow. Chemical potential is the driving force for mass diffusion, mass flow. Okay? Pressure is the driving force for mechanical motion. Those are all thermodynamic, intrinsic thermodynamic quantities: pressure, chemical potential, temperature. The other way to think about the chemical potential is it's the average energy needed to add particle into a system or take a particle out of the system. So first, chemical potential is energy. Look at this; it's the equivalent here. And second, it's the driving force for the mass transfer. So if you do, chemistry, you do mass diffusion, or you do batteries, this is a quantity you would be dealing with all the time. Okay, so this is microscopic, and now I'm going to apply what I just wrote down in the previous slide to molecules. Right? I have a box of molecules, and at equilibrium, temperature T. I take one molecule, it has a kinetic energy. I'm thinking about the simple kinetic energy of the molecule. Right? So it's 1/2 mv squared. Of that, the v molecule is say velocity is the three components: vx squared, vy squared, vz squared. So that's what I have there. And this is the energy. Remember, in the previous slides, we say this is now a constant temperature molecule in thermal equilibrium at constant temperature. So that's the statistical closed system I'm using. Okay? And this is the energy, that's a kinetic energy. And here is a probability, right? Probability, I have a normalization factor. So I put in the probability of this molecule having the velocity Vx, Vy, Vz. And then next step, I want to determine A. Determine that prefactor A. Right? What I do. The probability, so the molecule probability is the velocity is from minus infinite to plus infinite. I include every possible chance. Right? So if I include every possible chance, that's my normal, the way I find out this factor A. That's all the, say, velocity from negative infinite to positive infinite. And they should sum up to 1. They got to have the velocity in between this. And if you do this integration, you find your factor A. And this is the famous Maxwell distribution for molecules.
It should be a minus.
Oh, thank you. Yes. There is a minus. There's this minus down here. Thank you. Let's see the other one. Yeah. Yes. Please add a minus up. And here is the same problem. I just copied it. So now, if it's a probability, once you have a probability, you can calculate your observation, right? What's the average once you have probability? So I want to find the average energy, kinetic translational energy, motion, kinetic energy of this molecule. So here is the energy weighed by this probability over all possible velocities. Right? And again, it's an integration. You either can do yourself or you look at a table. And what you find out is a very simple result. E equals 3 halves kBt. Okay, Bose-Einstein constant. It's 3 halves kBt actually is a very good number to remember, kBt. But also is a fundamental. There is a fundamental principle, equal partition principle, which says if your microscopic energy is quadratic. So if you look at this, kinetic energy is quadratic is in velocity, mv squared, right? So if energy is quadratic, each of this quadratic terms contribute the average energy half kBt. So if you look at this molecule there, because it has 3 quadratic terms, so each contribute 1 half kBt. In total, it gets retained half kBt. So this is the equal partition principle. And now I would like you to get the idea of what is kBt. This is really something that if you want to have a microscopic mind, you should remember. How large is it? kBt, 1.3 10 to the minus 23rd, 300 degree Kelvin. I think I forgot to correct this again. No, this should be 4, not 5. 4.14, right? 4.14, and if you take a 4.14 divided by 4, that's a big number, so hard to remember. And people, again, different field, people use different ways, different measures, and one often used unit is electron volt as an energy unit. What is the electron volt? You have a charge, you apply an electric field, 1 volt, say under 1 volt electric potential, how much energy it has. So 1 electron volt is 1.6 10 to the minus 19 joule. So I translate this into at room temperature, 1 kBt is 26 milli electron volts. Okay? Now, think about if this is the average energy of the molecule, how fast they are moving. This is the molecule moving in this room. You can go to estimate right? Because this energy equals 1/2 mv squared. So you can go to estimate the energy, the velocity of the molecule. 1/2 cancel. You do the mass. I took the oxygen as an example. I know the number of say oxygen atomic number is 8, so it's 16 neutron proton, and each of the proton mass is 1.67 10 to the minus 27. Right. So number is about 200 meters per second. Depends on whether it's a light molecule, heavy molecules. So those are the microscopic molecular picture there. Right. That's about molecules. Let's think about the electrons. Molecule there, what do we say? We did not do anything quantum side. The Maxwell distribution is classical statistical thermodynamics. Now, when I do electrons, the quantum mechanics sometimes is very important. So let's think more quantum picture. From quantum mechanics, we learn, you have physics before, basic idea, I'm sure you all heard about. Energy levels are quantized, right? And this is some of you may still remember, if you have a quantum mechanical state, you can only have one electron, right? Pauli exclusion principle. And the quantum mechanics actually here I listed Planck-Einstein relation that gives the energy. This actually started from photon, so next slide I have more energy related to the frequency of the photon and the momentum related to wavelength of the photon. So that's the so-called Planck-Einstein relation. And what's in, again, this is another number. If you think about the quantum, you'll always see H Planck constant at 6.6 10 to the minus 34 joule per second. Okay. So now I'm going to look at one quantum mechanical state. And this quantum mechanical state can have a maximum of one electron, right? You could have 0 electron, you have 1 electron. And this quantum state has the energy E. Quantum mechanically allowable energy. When the electron is there, this state has energy E. When it's empty, no electron, the actual energy of the system is 0, right? But I only can have 2 possibilities. So I have these 2 possibilities. I sum this up. I want to find this A. The difference between the molecule I did before and here, for molecule velocity, I say, okay, from minus infinite to plus infinite, I include everything. But for the electron here, I only have 0 electron or 1 electron. So I sum this up to 1, I will find A. I'm not going, I leave the detailed math. So from the previous relation, I found A, and now I give you average. Again, I can give you the average energy because if I do observation, it's 0 or it's E. And if I do a lot of observation, it's an equilibrium state, say at temperature T. What's the average time, average energy, or average number of electrons? Right? Each individual observation could be 0 or 1, but there is an average possibility, right? So if I look at the average, again, say this is an n could be 0 or 1, and you sum up to Fermi-Dirac distribution. This is you look at that, what's the range of this f, the average? Huh? 0 to 1. That's you can't be above 1. This maximum is 1. Minimum 0. So it's between 0 and 1. And then you plot those, depends on the temperature. Right? And it depends on whether the energy of this level is above the chemical potential or below the chemical potential. The chemical potential is the, say, we said before, now it's you can think of this one quantum state that the open system, the electron can come in and goes out. The chemical potential is what's the average energy you need to take the electron in or put the electron. Take the electron out, put the electron. Right? So depends on whether it's above or below. You can say it's close to 1 or close to 0. Very narrowly distributed near the chemical potential. And in fact, if your temperature is 0, this will be a sharp transition at the chemical potential. Above is 1, and here below, let's say, above is 0 and below is 1. And the chemical potential at 0 temperature, there's a special name people give. Often they call that Fermi level. But in a lot of different fields, sometimes people just call Fermi level for any temperature. It's terminology convention. Okay, so that's for electron. Now we're going to lecture 2. We talk about molecule, we talk about electron. Next I'm going to talk about electromagnetic wave, the photons. Right? I mentioned before the Planck-Einstein relation is really looking into photon, and later on was generalized for any material wave. And so what we have is if there is electromagnetic wave at a certain frequency mu, what the Planck found is that the energy of that mode, the quantum mechanical state, at the time there was no quantum mechanics. So electromagnetic mode of specific mode, the energy has to be quantized, and basic energy quanta is h nu. And this energy quanta later on was called a photon. Okay? And what Einstein came in is saying that the quanta not only just say they have the wave, but also has a momentum. So this is where the wave-particle duality came from. So the momentum of the quanta is related to the wavelength of the wave, and again related via h. And so the each quantum state, the energy can only be a multiple of the h nu. Normally, when we think about the wave continuum mechanics, it can be any value. But the quantum difference is that the energy could be only multiple, so n is now integer, and it has 1/2. That's also called this 1/2. Normally, is not important. It's called 0-point energy, and it's really, if you still recall some quantum mechanics, that's the so-called Heisenberg uncertainty principle requirement. So this is 0-point energy. Normally it's not important, so I'm not going to detail much. So that's a photon. Okay. Now I'm going to. It turns out the whole photon. You can think of this as the electromagnetic wave. Now I'm going to talk about a different wave. That's the lattice wave, the atomic vibration. Right? The atomic vibration, now you can think about starting with classical mechanics. If you have mass spring system, the fundamental natural frequency is square root of k over m. Right? And of course, in classical mechanics, we say the energy is related to the amplitude of the wave, the velocity. And once you go to quantum, it turns out this wave, the energy cannot be any value, same as the electromagnetic wave, and the energy can only be multiples, same, you can say multiples of h nu. And now there was an analogy made for this quanta of vibration, and that analogy length is photon. Okay? Electromagnetic wave, the basic energy quanta is a photon. That is atomic vibrational. The energy, base energy quanta, is photon. Okay. So what's the statistically obey, right? At a certain quantum state, if you think about electrons, could be 0 and 1. Maximum is 1. And here, at the mole, at that frequency, it could be 0, 1 to infinite. So that's the difference. Electron, 0, 1. And here I could be any number, integer numbers. So I need to find the distribution average number of photon or phonon if I have an equilibrium system. Okay? Do the same thing. Right? I have the probability, and now if I have n photon or phonon in this micro state, the quantum mechanical state that has this specific frequency, that's the probability. I sum this up from n equals 0 to infinite. That still should give me 1, right? You have either 0 or 1 or infinite number, or the in between, somewhere in between. So sum up, I have 1, I will determine A, and this A, from this A, I go to find the average again. And once I find the probability, I find the average number, right? Same way as I did for electron. And this average number now is the Bose-Einstein distribution. And this Bose-Einstein distribution, if you compare with the previous Fermi-Dirac distribution, the only thing changed is the plus sign now goes to minus sign. And because of that, it's no longer between 0 to 1, it's between 0 to infinite. Right? And in fact, for photon and photon, because the number is not conserved, okay? It's not like an electron is a conserved number. So temperature potential concept is not called, is not a good one. So that's a 0, we think of the 0. And this is the distribution of Bose-Einstein distribution.
What's the reason for setting mu at 0?
It's not a conserved quantity. It's when we talk about mass transfer particle, that's a fixed number, right? Total number either going out or going, but that's a conserved number. Here it's not a conserved. But there actually, later on when we talk about the solar cell, you'll find out there's a quasi Fermi level getting into you here. So it's actually a very deep thing there. This is just a simple argument. Okay. And that's about now in this time frame. Like I said, you're probably familiar with classical thermodynamics. You're not familiar with the statistical side. Like you just take it. Okay, this is how the result we'll be using. What gets into mind microscopically, we have Boltzmann distribution. We have Fermi-Dirac distribution for electron. We have Bose-Einstein distribution for photon. That's what you need to know. Okay? And what we need, I'm going to summarize next. This is the heat transfer. Before was thermodynamics. Now, heat transfer, again, you take 2005, 2006, this is a very, should be very familiar. If I have, we have three modes of heat transfer, right? Conduction, combustion, and radiation. And describing the conduction is a Fourier law of diffusion. So the heat transfer rate, here I put the rate in watt. It's proportional to the area, proportional temperature gradient, and proportionality constant is the thermal conductivity. And that's a material property. Normally we think of that as a material property. And the negative sign actually take care of the second law. It says temperature, heat will flow from high temperature to low temperature. And You can do, that's per watt. You can do flux, that's per unit area based. So just normalize the area, or you generalize it into 3 dimension rather than write it into 1 dimension. So that's heat conduction. And convection is when you have fluid flow in the surrounding of, say, heated or cold surface. The heat transfer between the surface and the fluid is proportional to the temperature difference of the wall and the fluid. This fluid actually transition, the temperature goes from the wall to gradually to the center of the fluid or ambient. Right? And the proportionality constant here is H, the heat transfer coefficient. And but H is flow dependent. It's not a material property. Depends on how fast the fluid flow, and depends on the geometry. So this is a big topic in 2005, 2006. And we know there's natural convection, forced convection. So this is just in terms of the terminology there. So those are conduction and convection, and of course the thermal of heat transfer is radiation, thermal radiation. Right? Thermal radiation for black body, one single surface or black object, the emission is given by the Stefan-Boltzmann law as the proportional to temperature force power. The proportionality constant is Stefan-Boltzmann constant, right? So this is for black object. The real object is not black, so we use the emissivity to characterize it, and we'll discuss more down the road. Now, if I have 2 objects exchange heat, in this case it could be vacuum, right? That's the difference of radiation compared to conduction and convection, which requires a media, and here the heat transfer is by electromagnetic waves. So I wrote a simple form of radiation. The net heat transfer is the temperature force power. And remember here you have to use the Kelvin, not degrees Celsius. Look at the units and so on in Kelvin. And if the object is not black, we use the emissivity. And here is the effective between 2 surfaces because the 2 surfaces may be different. Like I said, we'll discuss more down the road. So those are 3 modes of heat transfer. Right? And in this course, we'll talk more on conduction. We'll talk more on radiation. You have learned a lot. Some of you learned a lot of convection, so that's probably clear, right? Now let's think a little bit more on conduction. If I have a 1-dimensional null heat generation inside, the heat flow is constant, so Q is constant. You go back to the Fourier law, you integrate it, you find out the heat transfer between the 2 points from this to the other side at steady state is proportional to thermal conductivity temperature area, inverse proportional to the length. So if you want to do thermal isolation, what do? You use a long object, use a small cross section, right? That's the thermal isolation. A lot of times when you design a thermal system, not only heat getting in, you also want to isolate it. And the R, we can combine all this right into thermal resistance, just a definition, because this way it looks very similar to electrical circuit, where your driving voltage is now the temperature difference, and your current is a heat current, and your resistance. So you can use the same way as you do circuit analysis. If you know the thermal resistance, this is for different geometries different, and even for convection, you can express, you go to do thermal resistance. So So you can build thermal resistor network to do some simple heat transfer. Okay. And another thing that's important to keep in mind is the order of magnitude. What are the good conductors? What are good insulators? Right? And the best conductor turns out is diamond. Why? That's because the bonding, the spin. So in this case, is the wave, atomic wave that carries the heat. So if the bonding between the atoms is strong, the spin constant is large, the velocity is large. So that's why diamond is a good conductor. And metals are not that good. Metals are by electrons. And insulators, you can say the wood, amorphous material, quartz, those are poor thermal conductors. Because the atomic arrangement is random, and the randomness make the wave harder to propagate in the material. Okay. So this is, again, macroscopic. Now I'm going to also give you the other view, microscopic view of heat transfer, heat conduction. And the kinetic picture. So what happens, how heat really is conducted. Let's think about the molecules. And the molecules, let's say we have a box, on one side is hot, the other side is cold. Let's forget about convection. How heat goes from one hot side via the molecule to the cold side. It's really, on the hot side, the air molecule, right, collide with the wall. And on the wall is hot, it means the velocity is faster. So this molecule will get a, faster velocity due to that energy exchange between the wall and the air molecule. Now, this hotter air molecule will collide with the labor molecule. Of course, they have a chance to go randomly. Every molecule is moving a few 100 meters per second, as we talked before, right? And they collide with the colder one, and they impart some of that excess energy to the next labor. The next labor go back and forth. Again, they do this cascade the energy from the hot to the cold side. It's a diffusion process. And typically, there's the distance of this collision, right? You can go to estimate it, and just turns out that this distance between the average molecule collision is about 100 nanometer. In this room, the air molecule distance between collision is about 100 nanometer. Okay, and so now I give you a few more definition. Right, the energy per particle, let's again take energy per particle as E, and the average velocity is V, and time between collision is tau, and distance between collision is gamma, that's a mean free path. So time is the average time between collision is relaxation time. And this distance and the time is related by the velocity. Right? So what is a heat transfer? When I think about heat going through this imaginary surface here, how I calculate it? I do counting. I will say, okay, only those molecules within one mean free path, Vx is the velocity component in the x direction, times the collision time, right? So only those molecules can go zip through the interface without collision, because tau is the average time between collision. So this part of the molecule is hotter, they go from this side to the other side, and on this side the molecule is cooler, again in the Vx times tau direct, they go from this side to the other side. Right? And I take the difference. I count all the molecules, I take the difference, that's my heat flux. So let me write down the math. That's what I do. I say, on the left-hand side, this is the per unit volume of how many? N is the particle number density. I forgot the second bullet's there. Each particle, how much energy it has, and this is the velocity in the x direction, right? So I say only in this range from x to vx minus tau. In this range, you can go through. On the other side is x plus vx tau. You can do more detail, but clearly this is a very simple argument, right? So that gives me local heat flux. You go check the unit is watt per meter squared heat flux. And then next, let's just do Taylor expansion of these two terms and write it into differential form, because this is about 100 nanometer. If I do meters or centimeter or millimeters, that's essentially continuum, right? Very small delta. So I do the derivative, and I do Taylor expansion. This one half is because there's only half of this go this way, half go that way, right? So that's where the half came from. And after I do the Taylor expansion, I have E and V, and Vx. Vx is random velocity. I pull out it's independent of distance. It could be dependent on distance. I'm just making an assumption, approximation. Independent of distance, this is Vx squared. Vx squared is random, so it's 1/3 of the average velocity. 1/3 of V squared. So that's my 1/3 of V squared replacing this Vx squared. Tau is here, and the N times E is per unit volume. How much energy, internal energy the molecule has, right? So I have this N times E is U, and I take a chain rule du dt dt dx. Okay, what do you get? You get Fourier law, right? Because here is 1/3 V squared tau C, and that's the thermal conductivity, and this is temperature gradient. You can do that. You can go back and do your Fick's law and Newton's shear stress law. In fact, all the diffusion law you learn in 3 steps.
But
yes?
you said we could move the velocity out of the derivative because it was constant.
Right.
But isn't the velocity related to the temperature?
Yeah, good question. This is later on when I discuss the thermoelectric effect, I'll come back to this. Okay. Here I'm talking about molecule, and I just want to show you the Fourier law. There are clearly approximation, and what they're talking is more like couple the mass and heat transfer. And in fact, if you learn once the heat transfer, you know mass and heat transfer couples. Okay, so the thermal conductivity is 1/3 specific heat, velocity, and mean free path. Okay, and the specific heat is per unit volume. If I do capital C, it's per unit volume base, and typically we do per unit mass base. It's just density times per unit mass base. Okay, so this is a very useful relation to keep in mind. Simple. The thermal conductivity depends on how many energy is stored by the molecule, how fast they travel, and how far they travel between collision. So if you want the high thermal conductivity, you want them travel far. If you want low thermal conductivity, you reduce that. Right? And for most solid, this C is about 10 to the 6th power. It doesn't vary by a factor of 5. So when I do on my back of envelope order magnitude estimation, I say C is 10 to the 6th. You go to check. And velocity in solid is just so you can roughly think of the speed of sound. Few hundred to few thousand meters per second. The mean free path is short, right? Nanometers, 100 nanometers. So that's the range order. Okay, so this is I think most of you probably in 2005 you haven't seen it. It's a very simple, but the picture is really the diffusion picture or similar. let me give you, I haven't quite finished relations. I come back to, I said the Stefan-Boltzmann law, right? And what I want to show you next is how I can derive Stefan-Boltzmann law from the statistics I just showed. So I'm considering enclosure. Let me even imagine the enclosure is perfectly reflecting. There are photons, and the walls is at temperature T. So it's an equilibrium system. I want to see how many the electromagnetic wave inside this box, how much energy they have at constant temperature, equilibrium, thermal equilibrium, right? So let's go back to a little bit the basic relations of electromagnetic wave. We know the speed of light is a proportional. It's speed of light is wavelength times frequency, right? That's high school we learned. And definition, I say angular velocity is 2 pi mu. Wave vector magnitude is 2 pi over lambda. What is the wave vector? The wave propagates in certain direction, right? And so it's because the direction is a vector. 2 pi lambda, lambda is a wavelength, it's a scalar, and the directionality gives the vector. So it's a kx, k by kz if you do Cartesian coordinate. And so I can write that the c equals mu times lambda in terms of frequency and wave vector is c times omega equals ck. So this relation between wave vector magnitude and the frequency is called dispersion. And in the speed of, in the case of light, it's a linear, right? C is 3×10⁸ meter per second. And of course, because of vector, so it's a square root of the components. So that's the dispersion. And now I want to count. My question is how much energy photon has inside this box, right? I'm going to count how many modes it has. Remember, each mode, the Bose-Einstein distribution already tells me each mode how many photons. So how many modes? So that's basically I'm counting, right? And mode, because I'm a perfect wall, so you can see the mode has to be standing wave here, either this way or this way. That is boundary is 0.
Why is it so? Why should it be so?
Otherwise, it doesn't get a steady state. It keeps propagating. Okay? So, this is my wavelength component in the x direction. Kx, right, is a corresponding wavelength in x direction. And the Lx is the length here, right? So if I just say this must satisfy the rule, then I have to have integer. Those are the possibilities. And that could translate in the possibility of my k. Kx is just 2 pi over lambda x. So this is n to pi 2 Lx. Okay. So each combination of nx, ny, nz, each set gives me one mode. And when I want to find out how much energy, I just sum up all those modes, right? So I sum that up. And remember, when I do molecules, I do velocity from minus infinite to plus infinite. And here, when I do this, I do discrete summation of nx, ny, nz, right? So I do this summation. This is a nx, ny, nz. Each mode has, this is the number of photon in this every set, and this is the energy of a photon is h omega. I got a factor of 2 because the electromagnetic wave is transverse wave, and it has two components, 2 polarizations. So that factor of 2 comes what it comes from. Okay. If you don't look at this, that's where my starting point. And what I want to do is, rather than do the summation, I'm going to translate it into integration. Summation is over n. So if you look at this interval between n and k is 2 pi 2lx. So when I have a dkx, I divide by 2 pi 2lx. That's n. If this is a large number. For small, you have a lot of problem. So I translate this summation in nx into this dkx integration. I do the same for ky, kz. This is I'm just copying. I wrote the extra step here just for the later purpose because my function is a even function, so I extend to minus infinite to plus infinite. The difference is a factor of 2, so I don't have this 2 here anymore because the factor of 2 is gone. Okay, that's just for my later purpose. The end result, this is just equivalent. And what it means, I can, rather than standing wave, I can say do 2 counter-propagated. One goes left, one goes right. That's when you do the maximum velocity is minus infinite to plus infinite. So that's equivalent. Okay. I think I will probably have to stop here. There are 2 more slides you can look at, but I'll discuss what's coming is the Blackbody radiation in each wavelength, how much energy carries, with simple this concept. Okay?